So we're going to be doing limiting reagent problems. And probably the number one question that I get at this time in the chapter is, well, when do we use the limiting reagent problems? When do we know that we need to do all of this work? Well, we have a clue. If we are only given one amount of a reagent, for example, we're given 3.25 grams of ammonia, and we're asked how much product can be formed, then it's just a straightforward calculation. We can use our bridge over troubled waters, and we can get how much NO is formed. However, if we are given not just how much NH3 there is, but also we're given how much O2 there is, now we've got two reactants, and we've got to figure out, well, which one do we use in order to calculate our amount of product? And that's exactly the problem we're in. We've got two of them. Only one can be used to calculate the amount of product. One of these reactants is going to run out first. So we need to figure out which one's going to run out first. That controls how much product is made. So if you're given more than one amount for the reactants, then that's a signal that you're doing this limiting reagent problem. So let's go ahead and look at a limiting reagent problem. It says here, in an experiment, we've got 3.25 grams of ammonia, and it reacts with 3.50 grams of O2. Now, I've already pulled out that information and put it on our chart here. Now, the questions that we are asked about are, what's the limiting reagent? How many grams of the product and O happen to be formed? And how many grams of excess reagent remain after the reaction? So we're going to use this method to do all of our limiting reagent problems. And we're going to start off with making sure we've got a balanced chemical equation. If that equation is not balanced, well, none of our molar ratios are going to be right. So number one, balance that chemical equation. After that, we're going to determine how much product we can get from each of the reactants. So we're going to do separate calculations to get the amount of product. You're going to look at the amount of product you get from each of your reactants and see which one has the lowest amount of product. The reagent that gives you the least amount of product, that's going to be your limiting reagent because it's going to run out. And then be sure to answer all your questions. You can see from this example that we can have a number of different questions being asked. And finding the limiting reagent is only the first step. Then you have to answer all those other questions. So let's go ahead and move over to this board over here. We'll focus in on this board over here so that we can actually work this problem. Okay. Now, I've gone ahead and balanced the chemical equation, and I've put our molecular masses, or our molecular weights, up here that correspond to each of those compounds. So when we need them, we have them. Hopefully by now everyone's very confident about calculating those molecular masses and molecular weights. So let's go ahead and calculate how much product we can get from your given reactants. So let's start off with NH3, and we're going to do this calculation. We're basically going to do bridge over troubled waters. So first we're going to go from grams of ammonia to moles of ammonia. Remember, all the vertical ones are molar masses. Then we're going to go from moles of ammonia to moles of product. And that's going to be a molar ratio. Any of the horizontal ones are molar ratios. Now, it doesn't matter which product you use. You just have to use the same product for both of your reactants. Okay. Now, I'm going to use NO because that's what's in the question. If water were in the question, I'd use water. So it doesn't matter which one you use, you should get the same answer as far as which one is limiting. Okay. So let's calculate how much NO is formed from this ammonia. We know how to do that because we've got that bridge over troubled waters. So we'll start off with the number they give us. We'll get our little grid up here so we keep our numerator and denominator separate. We're going to do molar mass first. Oops. Let's go ahead and tell us exactly what this is because we're dealing with multiple things. So we got 3.25 grams of ammonia. Molar mass, grams on the top. Where do grams have to be to cancel out? Well, they have to be on the bottom. So we're going to put our grams of NH3 over here. The molar mass, we've already got calculated, 17.03. It's always grams per mole. It's always per 1 mole. All right. Now we've got moles of ammonia. That's in the top. Where do we want it to cancel out? Well, it's got to go in the bottom. So we're going to put our moles of ammonia in the bottom. And what we're going to put on the top. So moles of NO. Now we have to get those coefficients. Okay. The coefficient for ammonia is 4. So we're going to put 4 right there. Coefficient for NO is 4. So we're going to put 4 right there. Now we've got how much product we're going to be producing. And we can go ahead and do that calculation. And we end up with 0.191 moles of NO. So that's how much NO we get if we use up all of the ammonia. Now let's do the same calculation for our oxygen. We start off with the number that they give us. It's going to be paralleling this calculation exactly. Okay? We're going to go from grams to moles of O2 and then moles of NO. So we've got grams of O2 on the top. Where do grams have to be to cancel out? Well, they have to be in the bottom. So we've got 32.00 grams of O2. Remember, that's O2, so it's 2 oxygens. Each oxygen is 16. So our molar mass of O2 is 32 grams per mole. And if you want to put that 1 in there, go ahead. All right, moles of O2 is on the top, so where does it have to be canceled out? It has to be on the bottom. So moles of O2, we want to go to moles of NO. So that's what goes on the top, moles of NO. Now we have to get those coefficients in there. O2 has a coefficient of a 5. That's what we write. NO has a coefficient of 4. So that's what we write there. Now we do this calculation. And we end up with 0.0875 moles of NO. Alright, so we've calculated how much product we can get from each of the reactants. Now we look at those and we figure out which one is lowest. Well, this one right here, 0.08, is lower than 0.191. Okay. So this is the lowest. So the thing that we use to calculate this is the limiting reagent. So we go back to the beginning. Here's our limiting reagent. O2 is limiting. If O2 is the thing that's limiting, then ammonia is excess. We run out of O2 when we produce this much NO, so we have no more O2 that can make any more, so we can never get up to that amount. So you can say this is not possible. So now all of our calculations will originate coming from O2 and the amount of O2 that's present. So let's go ahead back and look at some of our questions so we can make sure that we answer those. We have, what is the limiting reagent? Well, we've already determined that O2 is the limiting reagent. Now it asks for how much of the NO is formed. And it asks it in grams. Well, not a problem. We just solved how many moles of NO is formed. So let's go ahead and start with that. Moles of NO. All we have to do is change it to grams. Grams to moles, moles to grams. We use molar mass. Molar mass is 30. Moles is in the top, So moles have to be in the bottom, cancel out. Moles of NO. We put the other thing on the other side of the line, grams of NO. And our number happens to be 30.00 grams per 1 mole. These guys cancel out, and we're going to get grams of NO. Let's go ahead and do that calculation. We end up with 2.63 grams of NO. So now we found out how much product has been formed. We've done that second one. Now let's go ahead and talk about the third one. It asks us for how much excess reagent still remains after the reaction. So in order to figure out how much remains after the reaction, we have to know how much the reaction took up. So we're going to focus our attention back over here so we can figure that out. So we know that once the reaction has been made, we have used up all of the O2, and we've used up some of the ammonia, but not all of it. So we have to figure out how much of the ammonia we have used. So in order to do that, we're going to take the amount of oxygen. Remember, everything starts with the limiting reagent. We're going to figure out how many moles that is, how many moles that translates to NH3, and then we come back down to grams of NH3. It's that bridge over troubled waters again. All right, so let's go ahead and do that calculation. So first of all, we have 3.50 grams of O2, and we need to get it to ammonia. So we're going to start with our molar mass. Grams are on the top, so grams have to be in the bottom. It's 32.00, and it's always per 1 mole. Now, moles of O2 are on the top, so moles of O2 have to be at the bottom. We want to go to moles of ammonia, so that's what's going to be on the top. Coefficient for the O2 is 5, so we're going to write the 5 right there. Coefficient for the ammonia is 4, so we're going to write the 4 right there. Now here we've got to go all the way to grams. Okay, so we're going to put our molar mass on there at the end. Moles of ammonia is in the top, so moles of ammonia has to be in the bottom. And our molar mass is 17.03 grams per mole. We end up with grams of NH3. Let's go ahead and do that calculation. 3.5 times 4 times 17.03 divided by 32 divided by 5, and we end up with 1.49 grams of ammonia. That's how much ammonia was used in the reaction. So let's go back to our questions. Is that what it asked for? How much ammonia was used? No, it asked for how much remains after the reaction. So we have to do one more step. We started out with 3.25 grams of ammonia. We used up 1.49 grams. So we're just going to subtract those. We end up with 1.76 grams of ammonia, which are left or remain at the end of the reaction. We'll go back up and make sure did we answer all of the questions? Yes, so we're good.